Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so today we will continue with our discussion about light, more specifically about optics. So in optics we first looked at refraction, right? And so when we looked at refraction, we also looked at this idea called total internal reflection, right? Now, when we looked at total internal reflection, we said the following. Let me refresh you about total internal reflection first. But before I go into that, let me little bit explain about the JnanaMarga program. The JnanaMarga program requires students to, so let me give you a quick overview of how students go about, participating in our JnanaMarga program. So let me share my screen. Okay, so now I'm sharing my screen, and so when students participate in the JnanaMarga program, typically the student, they can use our YouTube channel, our YouTube channel particularly for students who are, in our program. They're all welcome to join, and they're all welcome to visit our YouTube channel. And what we have there, which is most invaluable, is our playlist. Okay. Now, our playlists have tons of videos, So if you look at our playlist, you will notice that we have almost 80 videos of chemistry, 80 videos of biology, and almost 75 videos of physics, and then 50 videos of maths. So these playlists can be used by students, to learn about the material, Now, in addition to the playlists, let me go back there. Okay. So in addition to the playlists, the students typically enroll in, I think by the time they reach the class 11, they would have made a decision about whether they're going to be engineering or in maths or in medicine side, Now, students who go towards our engineering programs, they typically download and install our flagship Ramanujan product. Okay. Now, what is important about the Ramanujan product is now that we also support, new, new today also assessment. Our assessment platform is excellent. Now students should download Ramanujan, or if they have, if they are in the, if they are going to be NEET students, they should download our Sushruta platform. Okay, these are both trademark platforms aimed at the Indian market. So you download one of these platforms, and then once you've downloaded the platform, you install it. So you do install here on an Android phone. We do not work on iPhones. You get an Android device or an Android, preferably tablet. So once you download, you then install, our platform. So typically you can go to the site and you can watch the video, and that video will give you a very good view of, what is in the platform. And so typically what you do is you use the app in the following way. The app comes with both the textbook, and in this case the NCERT textbook. The NCERT textbook is the Bible for students who study for NEET, most notably for biology. The NCERT textbook is everything. You should not go and say, I want to study some other textbook. Just go with the NCERT textbook when you study for NEET biology. Okay, and for physics, typically also the NCERT textbook is very useful. But most often we recommend that the students buy our tablet solution, or they make use of H.C. Verma. Students, of course, can use also Resnick and Halliday, but this is H.C. Verma. Okay, this is part one, and there are two parts to it, part one and part two. Okay, so you purchase a copy of H.C. Verma, and you can also use our app to find out which chapter, how to study and all that. Okay, so now you use the textbook, you use the videos, so the textbook and the videos complement each other. The videos are in context in the JnanaMarga app. So then you use the slides. The textbook, the videos, and the slides, they form the core of the app. Now, in addition to this, you use the YouTube channel that we have. So using these four elements, you learn the material first. Then now we have added assessment. So then the student takes advantage of the assessment part. They do self-assessment first. So you do self-assessment in chapter by chapter, unit by unit, and you keep doing self-assessment. You keep learning better, improving, and doing self-assessment. Now, we also now have Guru Diksha program for students who want to access, our, want one-on-one mentoring with our teachers. This is also very useful for many students. Many students, should start with this and then plan for Guru Diksha. If you are going to be taking KVPY, you must plan for, and become a top ranker there, etc. You must be getting yourself ready using the Guru Diksha program. So send me an email, Srini, SRINI at JnanaMarga.in. Okay? SRINI at JnanaMarga.in. JnanaMarga.in. Okay. So now we also have the Nyana test prep. This is for advanced students who have already, taken advantage of the assessment and improved their scores, and they are confident. At this point, you come to Nyana test prep, and then you take timed tests, 3-hour tests. You never kid yourself by the time you take timed tests. You can also complement it with what you get from Diksha and what you get from Swayam. The additional platforms that are available. Okay, so you can take tests there and you can take tests here. So that's how you use our program. Our program is meant to be an affordable answer to the problem of JEE and NEET. You don't pay the 2-3 lakhs a year that some students pay, or you don't go to Kota and live there and have to pay the costs associated with that, and then also the learning associated. Okay, so you learn at home, you go to your school, you study from your teachers, and then you use the Nyana platform. Okay, so this is for students whose schools are not associated with us. Okay, students whose school is associated, we have a slightly different answer also. Okay? But this is for the broad section of students. Okay? So that is how the JnanaMarga program works. Okay, so you must pursue these in sequence, and you must stay with the program. Every week you must plan to attend the lectures. These lectures get uploaded into the playlist, and you must use the playlist as well. We are not on and off, nothing helps. You want to be a top ranker and compete with the best in India, on and off, nothing will help you. Doing anything on and off, nothing will help you. So first, today I'm going to start with, as we continue the discussion, we did reflection, refraction, and then we looked at, mirrors, not mirrors, lenses, right? So then we looked at optical instruments, and then we discussed how in the case of a telescope is different from a microscope, and then and how they are different. So today I'm going to do a refresh of what we did for total internal reflection little quickly, because we are getting going into reflection optics as well. So firstly, how does when is there refraction? When is there total internal reflection? Typically, as we said, right? If you have ordinary glass, you will have both at reflection and refraction up to a certain angle. Okay. Now, beyond a certain angle, there is, see, like if you see this image, right? There is a little reflection and there is refraction. That is, the light goes into the medium. So assume medium 1 is air, medium 2 is glass, right? In the normal case, you will have a little bit of the light reflected and quite a significant portion of the light going through a transparent medium refracted. Okay. Now, and what is the law that governs the reflection and the refraction? The law that governs the reflection and the refraction is that sine I by sine R, right, is typically the refractive index. Okay. So incident angle sine I by sine R is is N2 by N1. Okay. So typically, right, when you have in this case, right, here we are, notice this case is little different. N1 is greater than N2, right? N1 is greater than N2. That means this is glass and this is air, unlike what I said before, right? So when you go from a medium to air, right, what happens is that's when you have this sine I by sine R, right? See, N21 in this case is N2 by N in this case is N2 by N1, right? N2 is rarer. So N2 by N1 is less than 1, right? So N1 is what? N1 is glass, right? Its refractive index is about 1.5. N2 is air. What is that? Refractive index is 1. So N2 by N1 will be less than 1, right? So sine I by sine R in this case, right, is going to be less than 1, right? The incident angle is going to be small. The refractive angle is going to be bigger. If you just extrapolate this, it will go somewhere in between, right? So now in such situations, right, as the refracted angle extends, right? So if the light was at a complete angle, it will get refracted. It will go through refraction up to a certain point. But there is one angle called the critical angle, after which it will completely be reflected. All the light will reflect, and that's why it is called total. Okay, every ray of light will then reflect completely. Now, what is that angle? That angle happens to be what is called the critical angle. The eye at which total internal reflection starts is called the critical angle. What is the least angle? And for every angle after that, there will be total internal reflection. Okay? Now, what is that critical angle? It is the sine inverse of 1 over n times the median. Okay. Now, the 1 comes from the the refractive index of air. Okay. So when you go from IC to air, right? There is an angle at which the refracted angle will become 90 degrees. Okay. When the refracted angle becomes 90 degrees, there is all the light will start to reflect. Okay, and so that is the critical angle. Okay, the sine inverse of 1 over n. So if n is 1.5, the sine inverse of 1 over n will be the critical angle. Okay, so that is when total internal reflection begins. When the angle of incidence is greater than the critical angle, total internal reflection happens. The entire incident energy is reflected back and no refraction takes place. Now, consider this laser beam. Okay, this laser beam is going to a certain type of glass. Now, we also discussed this anti-reflective coating, right? The anti-reflective coating, or in certain cases, it is to prevent it's to decrease the amount of light that gets refracted. It is to push most of the light into the medium, okay, the anti-reflective coating. Now, certain kinds of prisms, okay, are used, and these are used in cameras and many different places. They are used to make the light kind of, to be retroreflectors, and so what they do is they in this case, for instance, the laser beam is experiences total internal reflection. It goes in like this, at this 45-degree angle, which is higher than the IC. The IC is about, say, 41 degrees for this particular medium of glass, right? So, you look at this formula, sine inverse of 1 over 1.5, right? So it is whatever that angle is, and therefore in this case at 45 degrees, it is getting reflected. Okay, and so when you have two such reflections, the light that goes in, and you have this 45 degrees. Why 45 degrees? Then parallel light will come completely back, almost as though it's it's being as a retro reflector. Okay, so retro reflection is when you have 45 degrees as the this line is at 45 degrees. Okay, this is a 90 degrees, 45 degrees, 45 degrees. So parallel light comes, hits it, okay, and then it returns back. Okay, so that is a retro reflector case. Then we also discussed this idea of optical fiber, right? In an optical fiber, there is ongoing total internal reflection, and how does that happen? There is a inner core, okay, which has a different refractive index compared to the outer material. Okay, the outer material has a lower refractive index. That's when you have a total internal reflection, right? The outer core will have a lower refractive index compared to the inner material. Therefore, light which is just getting, which is of a certain angle, the light is introduced at a certain angle to make this total internal reflection happen, and it just gets reflected. Okay, so that's how this whole thing works. And these optical fibers are used very often in transmitting huge amounts of data from one place to another. In India, a lot of the railway lines, next to the railway lines, they put a lot of optic fibers because they got right of way throughout the country, associated with the railway line. So along it, they thought that maybe one can use a lot of optical fibers. But also across the country, there's a lot of optical fibers. So now, in addition to that, optical fibers are also used in, like for instance, endoscopy. An endoscope, what they do is it is done by a doctor called a gastroenterologist. In endoscopy, they will put that light scope, and they will have a sharp light. They'll put an optical fiber into your stomach, and then they will take a look at what else is going on in your stomach. Okay, when you're, of course, after they knock you out, typically, they'll give you an anesthetic, knock you out, then put a optical fiber into your stomach. This I want students who are going to be doctors to learn about this. Okay? So, and so typically what they do is they will find some kind of single wavelength light, coherent light, single wavelength, which they use. Okay, so those are all the users, and of course, optical fibers also used in a lot of sensors, optical fiber sensors, and of course, there is also lasers. Okay? Then we also discussed endoscopy. Okay? Now, mirage is also occurred due to total internal reflection, as we said, right? And now there's another kind of fiber which is often used, and that is this graded index fiber. Graded index fiber actually can carry more data than a regular fiber, but both with the step index fiber. This kind of fiber is called step index fiber. So there is a step in the index. So part of it is one index, the other part is a higher index. Now, graded index fibers, they have a slow variation of the refractive index, and they also use successive application of Snell's law. The index, from the core to the outer, slowly declines. Okay, the index will slowly decline. See, n of r is going down with y. So now they take a cut of it, and as the radius goes up, the refractive index declines. Okay, and so you can see the n of r. That's why they say n of r. Okay, so so this is a cross-sectional idea that you should get. Okay, with the way think of this light curve. Okay, so similarly, mirages also happen because of total internal reflection. You tend to see something which is very far away, almost as though it's near, because of the variation in the refractive index in air. And so there is so close to water typically, or close to, in places where there is you kind of get a apparition of some sort. Okay, so that's how you end up with the mirage. Okay, so I did this deliberately. So this is for students who miss the the part of total internal reflection and its relationship to refraction, because now we are going to go into reflective optics. Okay. So with respect to reflective optics, there is no sin I by sin r. There's basically incoming angle is equal to reflected angle, right? So that's very straightforward. So let's go there and let's try to understand how reflective optics works. It's pretty straightforward. Reflective optics is far easier than refractive optics. Okay. So typically, how does reflection happen? It's very straightforward. Let's say you have a plane surface, plane mirror, mirror on the wall. Who is the fairest of them all? How does it work? Incoming light, incoming angles, theta I, or reflected angle, theta r, theta I equals theta r. Angle of incidence equals angle of reflection, right? Now, how does it? We are going to very soon look at how it happens in a curved surface. In a curved surface, you think of the curved surface as a series of tangents on the mirror. So if you had a what is that? A circular, arc in a circle, right? Most curved mirrors are arcs in a circle, right? So if you have an arc in a circle, you draw the tangents, and then it will the optics will work in that way. Okay? Now, when we look at sunlight, right? We already discussed sunlight as carrying a lot of wavelengths, right? And when sunlight comes from a far distance, it's coming parallel, therefore, and if you have a mirror and it depends on how you've tilted the mirror. Okay, you can tilt the mirror in such a way to reflect it. And the most common material, they, of course, as many of you know, used in mirrors is mercury. Mercury is a metal, and otherwise if it shines, right? So they use glass, and inside the glass they have a coat of mercury, and then they or sometimes they use some other material also, you know. And of course, you can also have very well shined, you know, steel, etc., you know, which also shine a lot, you know. That's why everything, metals typically shine, you know. Not all of them, you know, not all of them are white, right? You know, the metals, you know, stainless steel, even aluminum is somewhat shines, you know, or titanium, etc. It is a circular section, you know. So now let's look at this idea of the concave mirror. Okay, now the concave mirror, right? The incident angle, right, gets reflected, right? So when you have, you know, like, see this, there are, first let's discuss the various things in this picture. Okay, the mirror, PQ is the mirror, right? Now this is the you know, the called something, you know, line of curvature, I think, you know. So this line, right, passes through the center. This line is the radius which passes through the center of curvature of the mirror, and that center of curvature of the mirror is called C. Remember, this is an arc in a circle. Okay, PQ is a part of a circle, arc in a circle. Now, the reflecting coating, right, will allow for no will not allow the light to go anywhere but be fully reflected, you know. So now you take this ray of light MP, right? MP is parallel to the line of curvature. Okay, now when MP is parallel to the line of curvature, on reflection it will go through this point F, which is called the focal point. Okay, now where is F? Okay, where is F? So now this is C, right? C, if you draw the line C, right? So it will, you know, cut this parallel line, right? So this angle will equal, okay, that angle. Okay, and this angle, for this angle, PC, let us call this point O, PCO will equal MPC. Okay, PCO will equal MPC. Okay, and similarly, CPF, right, will equal MPC. Okay, so why is that? Because C is the center of the circle, and if you draw a tangent here, that will, the CP, that tangent will be 90 degrees from what you learned in geometry, right? That's the geometry of a circle, right? And so this is a spherical mirror. Okay, so F is called the focal point of this spherical mirror, and this distance FO is usually denoted by little f. Okay, now the ZOC, which is the radius of the mirror, is denoted by capital R. No, and so typically the ratio between the this one, V divided by, will equal V divided by U. Okay? Now, what is V and what is U? V is this is U. Okay, this distance is V. Okay, so 1 by U plus 1 by V will equal 1 by S. Okay, and so you know, and typically that is how the geometry of all this works. 1 by U plus 1 by V equals 1 by F, and V by U also equals the corresponding magnification. What is the magnification? The magnification is the length of this divided by the length of this. Or what is that? The V by magnification is the length of the image or this divided by this. Okay. So sometimes it shrinks, sometimes it expands, right? So when does it shrink? When does it expand? We will find out soon. Okay. So now, in the case of a convex mirror, right, it's a little bit different. Okay. The incident light is when it's, because the mirror is like this, it's reflected, it will go that way. Okay. And therefore, most often what will happen is, now see, notice that in a concave mirror, the image is inverted, but it is real. Okay. In a convex mirror, the image is not inverted, but it is virtual. Okay. So you remember that. Okay. Now, typically draw a tangent and then normal to the tangent, so you form the surface. Okay. So the normal to the tangent is this line MC. Okay. The tangent is there, right? And therefore, theta r will equal theta I, where this is the line that divides the incident and the reflected angle, right? And we already discussed that theta I equals theta r, law of reflection, right? So now, in a convex mirror also, the same thing happens. The incident angle and the reflected angle are like that. Okay. So now, when does the mirror, right? When does the mirror produce bigger images and smaller images? That we are going to look at. Okay. So under certain circumstances, the image will become bigger. Certain circumstances, the image will become smaller. That is entirely based on the distances with respect to each other, right? V by U, we already discussed, is the magnification, and V by U will give you the ratio of V and the ratio of U. How close it is to the mirror, how far it is from the mirror, will give you the corresponding results. Okay, and so the V, the greater the V, right? 1 by V plus 1 by U equals 1 by F, right? So whether it's virtual or real, etc., they will change, with respect to the sign. Okay. So pole is the geometric center of the spherical surface. That is called the pole. The principal axis is the line joining the center of curvature, pole, and the focus of the spherical mirror. Okay. So this is called the principal axis. So principal axis, and this is called the pole. Right? Ray of light incident on the principal axis is reflected along the same path. So if you went through the principal axis, it will come right back at you. So the incident and the reflect angle will be both 0, right? Theta I equals 0, and theta r also equals 0. So this is all the simplest parts of reflection optics, right? So in reflection optics, parallel lines, all the parallel rays all of them will go through the principal focus of the mirror. Most often, principal focus is midway between the center of curvature and the point P, right? Pole, midway between the center of curvature and the pole, most often. So for convex mirror, in a circular one, okay, for a convex mirror, this is what happens. Okay, the center of curvature, or the principal focus, will be on the other side. Okay, therefore, typically the images that are formed will be virtual. So now, paraxial approximation, it means from the Greek word para, which means close axial means paraxial means lines close to the axis. Okay, para means close, axial means axis. So paraxial means close to the axis. Very different from, say, your Hindi word, right? Which is originates in Hindu spirituality. This is not like that. Para means close. Okay. Here we use approximation for small theta, sin theta equals theta, or tan theta equals theta. So that is a paraxial approximation. Okay. Only rays close to the axis pass in an optical system. Okay. Hence, an optical system deals with paraxial rays. Now, what is the focal length of a spherical mirror? Right? Focal length of a spherical mirror, QP equals R by 2. Okay? So for paraxial rays, point M is close to point P. Okay? So for such rays, QP equals R by 2. Therefore, QP is the focal length. The point P, Q is called the focus. Therefore, S is typically R by 2 for rays close to the center. So remember the paraxial approximation. Okay. That is called the paraxial approximation. The rays close the axis pass in an optical system. Okay. Hence, it deals with paraxial rays. Okay. Therefore, so here theta I equals md by r. Therefore, this applies only in this particular case. Okay. So rays inclined to an angle to the principal axis. The rays which are inclined to an angle to principal axis get focused to a point which passes through a plane passing through the focus. So if it was parallel like this, they get they pass through this plane. Okay, this plane is known as the focal plane. Okay, so what is the focal plane? The rays which are inclined to an angle at an angle to the principal axis get focused to a point which passes through a plane passing through focus. We're talking about Q here. Okay, this plane is known as the focal plane. So that is the initial part of reflection optics. So now we are going to next deal with the mirrored side of principle of this. Okay, so now we are going to look at the mirror equation, and although I already explained the mirror equation to you, because we've already done refraction optics and very similar to refraction optics. Again, these links that we provide, right, they are there only for your own understanding, but they're all from the IIT PAL lectures. And these are where all the material comes, and also from where you will get the most benefit by listening to the IIT PAL lectures as well. They matter as more than what we teach. Okay? We teach quickly so that the student gets a quick idea. Okay. Now, rays parallel to the principal axis will pass through the focus. Okay. So we're talking about one. One is parallel to the principal axis, and all those rays will pass through the focus. So if you had another ray here, that will also pass through the focus. Another ray here, that will also pass through the focus. And all those rays will form an image, okay, of AB as A prime, B prime. Okay. Now, this point will be this point A prime. This point will be this point. Let's call this point C prime. Not okay. D prime. D. Okay. This point is D. It will go hit this pass through the focal point, and then it will go there, B prime. So you will have, and of course, B, the ray which goes from B will go hit the P, and then it will come right back, bounce right back. So it will be B prime. So AB will form and will be inverted, and it will form A prime, B prime. If this is A, this is A prime. If this is B, this is B prime. So it will form a inverted image in a concave mirror. In a concave mirror, you have an inverted real image formed. Okay. Now, if the object is behind the center of curvature, then you will have a real image. Okay, have a real inverted image. Okay, now if the object is before the focus, okay, now if the object is between the focus and center of curvature, right? Between the focus and center of curvature, it will be an inflated but real image. So behind the center of focus, it will be smaller, right? Now, if it is between C and F, then it will be behind you. It will appear to be behind you, right? So if it is, beyond the center of focus, it will appear to be in front of you, inverted, right? If it is behind you, then it will be, if it is in between the C and the F, it will be behind you, okay? Now, if it is between F and P, it will form a virtual image, but it will not be inverted. It will be virtual and in the same direction as the original image and bigger. Okay, so very close to a concave mirror. If you go put your face right there, it will look like it is, you are inside the mirror in the same direction, right? And you will be huge. Okay, this is how reflection optics works. Now, if you are at the object is at the center of curvature, you will form an inverted image and of the same size. Okay, so now, reflection by a concave mirror, UVH, height of the object versus height of the image, right? Typically, that will be the ratio of the distances. V by U will give you the magnification. Okay, the sign convention in a convex for a concave mirror, right, is that everything is either positive. Everything will be, you can either take everything as positive or everything as negative. Okay, so here he is taking everything as negative, right? He makes the concave mirror like that, right? And therefore, because the concave mirror is like that, and he's saying this is X, right? This is positive X, so everything is negative for him. Okay, therefore, the heights. This one is H and this one is minus H. Okay, so now, so the mirror formula, he's now going to derive the mirror formula. Okay, and first let's go to the mirror formula. This is the mirror formula. Okay, 1 by V plus 1 by U equals 1 by F. Okay, so how does he derive the mirror formula? Okay, so he is using similar triangles. Okay, he is saying that the triangle ABF and FMD are similar. Or see, A prime B prime F, this triangle is similar to F and D, this triangle, right? That makes sense. These two lines, A prime B prime, is parallel to this line. Therefore, this angle is equal to this angle, right? This line is perpendicular to this. This line is also perpendicular to the same line. They're also parallel, right? So you have, so you have all these angles becoming equal. AAA is the case here. 90 degrees, 90 degrees. This angle is equal to this angle. Therefore, those two triangles are equal. Similarly, A prime B prime P. A prime B prime P. This triangle and ABP. Those two triangles are also similar. So as a result, he gets these two results. Okay, so because these two triangles are similar, he therefore gets A prime B prime divided by MD equals B prime F divided by FD. And and so from these two results, what he then does is he therefore says for small aperture, D is close to P. Okay, and therefore he says FD equals FD. So small aperture always paraxial approximation, right? FD, he says, roughly equal to FD. Therefore, BF equals BP minus FD, and using that, he derives 1 by F, 1 by V plus 1 by U equals 1 by F. Notice the small aperture D is close to P approximation used. Okay, therefore, 1 by V plus 1 by U equals 1 by F in the case of concave mirror, right? V, U, and F are all positive, right? So, so now what about the magnification? The magnification is the ratio of the H prime by H. What is H prime? H prime is the size of the image. What is H? H is the size of the object. So ratio H prime by H is the ratio of the, represents the magnification. H prime by H equals negative V by U. Okay. And the negative, where does the negative come from? Because it's inverted, right? Magnification is negative, forms real and inverted image. Okay. Positive, it means it's a virtual and erect image. Okay. So, so notice that. Okay. The magnification is negative, means real and inverted image. Magnification greater than 1, we say magnified image. Okay, less than 1, we say it is demagnified, or becomes smaller. Okay. Now, this is a convex mirror. Okay. In a convex mirror, when you are close to the convex mirror, right, the object will appear inside. Okay. Where do you use a convex mirror? Most often, you use a convex mirror in a car or a scooter. Those mirrors are typically convex mirrors. Okay? So most often, then you will have a light, incident light is coming from behind you, right? Hits the mirror on. I hope you see why I am pointing, because see, in the United States, we have the wheel here, the passenger is there, and therefore you look at this mirror and that mirror. Okay, the three mirrors, right? One is the flat mirror here, and the two convex mirrors, right? So now in this mirror, right, you have incident light coming from all these cars on this side. Then on that mirror, you have incident light coming from all those cars going that way. Okay, so now while you're driving, an image of the car behind you, right, based on the incident light, is going to be formed inside the mirror. As the car comes, right, it will suddenly become big. No, I don't know if you've seen that. No. So, but again, the same rules apply. 1 by V plus 1 by U equals 1 by F. Okay. The only thing is that the H prime by F, H is now the image that is formed is now virtual. Okay, and so that is the main thing that you must learn. So the car appears to be coming towards you, and then it interchanges. Okay, so you must notice how that happens next time when you are the passenger, not when you are the driver. Okay, and so take a look at that and then learn this formula. 1 by V plus 1 by U equals 1 by F. V divided by U is equal to the magnification H prime by F, right? And then remember these conventions. Okay, the image is inverted and real, or it is virtual and magnified. Okay, So these are the different ideas in convex mirror. My suggestion is that you spend some time reading the material in your NCERT textbooks, as well as taking a look at H.C. Verma, and subsequent to that, do some problems from our app, and also you can do some problems from, maybe go to a site or two and then do some problems. And of course, the best place to do problems is also from, the solved problems in HC Verma will also help you a lot, So these are the three places you can do problems, and of course your NCERT book also, So once you've done some solved problems in HC Verma, you then attempt the problems after that, the unsolved problems. And then if you have any questions, you come to the next class and then you ask me. That is one way to clarify your doubts. Okay. Now the other way is, is to, you can also email me, srini@jnanamarga.in. Okay, and you can reach out to us. Okay, but this is roughly all the different ideas that we introduced in today's lecture. You have basically the mirror equation. You have the how reflection works. Theta I equals theta r, and then how the magnifications are related to the distances from the u and the v. Right, the u is the distance of the object, and the v is the distance of the image from the mirror. Okay, so keep all that in mind and understand the optics of mirrors. Okay, so now with this, I'm going to wind down optics. I will look at polarization, but I'll look at polarization in the class 12 class, because that's where we discuss the electromagnetics of light. And then we are going to move on to the next set of items for class 11. Maybe although they do heat in class 12, I am next going to look at maybe some amount of heat in the context of class 11. Okay, so because in class 12 we are going to move on to more modern physics. Modern physics requires a lot more lectures. Okay, so I cannot do heat also there. So I'm going to do more heat. There's so much material in modern physics. It's all very difficult and quite complicated and intricate. So that's why I'll try and do some heat in the class 11 class, and then we will look at modern physics in the class 12 class. Okay. So with that, I'm going to stop. Maybe we'll do a few problems next time, but again, that's not guaranteed. We'll do a few problems relating to light. So I'll try and ready a small set of problems dealing with light. And then we can take a look at some of these simple problems, with respect to light. Okay. So remember, the main salient points of light are like this: waves, okay, and periodic motions. We dealt partly in the other class as well, the class 12 as well. Then we looked at refraction. Then we looked at refraction optics. Then we looked at telescopy and microscopy, right? And then we looked at mirrors and reflection. Okay, and when we looked at refraction, we also looked at Snell's law. But on top of all this, we also looked at the wave nature of light, dispersion, diffraction, right? The wave nature of light, diffraction, and also dispersion, which is the breaking up of light into its constituent waves when light is made up of multiple constituent light, right? And therefore the dispersion comes only in such cases. Okay, so light in various forms we have looked at, various aspects associated with light. These are all the aspects that deal with mostly with light. Polarization is another aspect, but that, as I explained, we will be looking at it a little more in the context of the class 12 material. Okay. So with that, I'm going to conclude today's class. We will meet again next time, and then let's try to, get going a little bit to the heat, and then we'll try to wind down all the material which we have, associated with with the class 11 here. The Saturday morning lectures deal with class 11. So so there is one additional chapter that Professor H.C. Verma discusses, and that one deals with photometry. My suggestion is you read that chapter. It is a small chapter, only 6-7 pages, or maybe 3-4 pages. So take a look at that chapter, radiant flux and luminosity. So please take a look at that chapter, and Lambert's cosine law. Very small chapter. So I'm going to leave that to you to understand. There is also another chapter on the speed of light. Maybe we will take a brief look at that when we get a chance next time. Okay. So we'll do a little bit of that before we move on to the material associated with heat. Okay. So or actually we will do a little bit of fluid mechanics before we go to the material associated with heat. Okay. So that you get an idea of all the various things that deal with such with fluids. Okay. So let's do that. Let's do a little bit with with fluids before we move on to heat. All right. So with that, I'm going to conclude today's class, and I'll see you all next time. So thank you very much for